What's up, everyone? Back with another Tesla Mechanical Design Engineer interview question solved. Following an initial phone screen, Tesla screens candidates using a Codility engineering exam, and this question came from that exam. Like my last videos, we're going to break this problem down into smaller steps, but the steps are going to be a little different. Step 1 is going to be review the problem statement. Step 2 is going to be cover the background topics and the equations that we're going to be using to solve the problem. Step 3 will be attempting our solution. And step 4 is going to be going back and reviewing, making sure that everything checks out. So let's kick it off with step 1, reviewing our problem. In today's problem, we are going to look at a thermal resistance network in steady state and find out how much hotter temperature 1 is versus temperature 3. Here you can see the thermal resistance network in the problem. There's a power source of 10 watts. Think of watts like a speed limit for vehicles, maybe a Tesla Model 3, except it's the rate at which electrons are traveling through a circuit. In this case, 10 joules flow through the circuit per second. As you can see in the diagram, the problem also deals with capacitors, resistors, and temperatures. Now that we have an overview of the problem, let's move on to step 2, covering the background topics. The first concept to be familiar with is Georg Ohm was the first to recognize Ohm's law in 1827, and that's the person you see here. What Ohm's law states is that voltage is equal to current times resistance. Sometimes you'll see this as current is equal to voltage over resistance. This establishes the proportionality between voltage and current across two nodes or points in a circuit. However, the problem we're dealing with asks for temperature, not the current or resistance at a point. So thankfully, Ohm's law can actually be modeled for thermal networks. So instead of voltage is equal to current times resistance, we have this analogous form of Ohm's law, which is that our temperature at point 1 minus our temperature at point 2 is equal to our heat flow rate times our thermal resistance. Here you can see the heat transfer equations for conduction. Heat transfer rate is equal to our temperature gradient divided by our thermal resistance. Thermal resistance is equal to the plane thickness divided by the thermal conductivity coefficient times the area of the surface conducting heat. So to solve this problem, you can see that the heat transfer rate would equal TL minus TR over our resistance. And our resistance for this thermal network is both R1 and R2 added up in series. The final concept that we need to familiarize ourselves with before attempting this problem is capacitors. So initially at time equals 0, capacitors have no voltage. After some time has passed and the circuit is at steady state, capacitors act as open circuits. They're fully charged, so they no longer let current flow through them. This is what the same circuit looks like at t equals 0. You can see the voltage is also 0. So the capacitors are charging, they act as shorts and allow all the current to flow through. At t equals steady state, the voltage of the capacitors is fully charged. Therefore, the capacitors act as opens. No current flows through the branches with the capacitors. Now that we've covered the main concepts required to solve this problem, we can start step 3, attempting the solution. We've already covered all of the equations we're going to need. We're going to be using Ohm's law, the modified thermal version of Ohm's law, and we're going to combine the two to come up with our own equations. So Ohm's law states that V equals IR. The thermal modified version of this equation states that the temperature gradient between 2 points is equal to the heat flow rate times the thermal resistance. And we are looking for the difference in temperature between T1 and T3. So we're going to say T1 minus T3, the temperature gradient that we're trying to solve for, is equal to our power, Q in this case, which is equal to 10 watts, and we can use this because it has the same units as our heat flow rate, times our resistance, which is going to be 5 Kelvin per watt plus 10 Kelvin per watt, because we're adding up the series resistances. So T1 minus T3, our temperature gradient, is equal to 10 watts times 5 Kelvin per watt plus 10 Kelvin per watt. Or temperature 1 minus temperature 3 is equal to 150 Kelvin. So T1 is equal to T3 plus 150 Kelvin. Now, I should have said this earlier, but it's important to note that because this circuit is at steady state, the capacitors are acting as opens, meaning we can essentially ignore them. So let's move on to step 4, doing a review of our solution. Notice the units cancel out and we're left with T1 minus T3 equals 150 Kelvin. This is great news because we know we're left with a unit of temperature. And we are left with temperature 1 in terms of how much hotter it is than temperature 3. So that's exactly what we're looking for, and we can feel pretty confident in this solution. There you have it, another Tesla Mechanical Design Engineer interview question solved. If you found any issues with my solution, please leave a comment below. If you solved this problem another way, also please leave a comment. I'd love to see how you did it. Thanks for watching, and I hope you'll tune in for the next one.